If you have any possibilities of turning on the camera, every time I'm very happy, because if I talk to nobody, which means just names on the black screen, it is a little bit difficult for me. But due to some limitations, I know that it can be difficult sometimes. Nevertheless, if there is such a possibility, I'm happy. Maybe just this. Okay, so next lecture of discrete mathematics. Today, I would like to talk about recurrence. Recurrence, today's topic. Recurrence. Of course, we know recurrence as a method of programming, but this is very, in general, this is very powerful tool for describe the behavior of some sequences in time, which depends of the previous state. Of course, in mathematics in general, this is connected with such a terms as Chebyshev and some probabilistic approaches, probabilistic terms. But in our applications, in our designing of the discrete focusing methods and behaviors, we'll describe it as a little bit more computer science dependent things. I will start from the example, because it is very, very helpful, which is known in literature as Hanoi towers. Of course, in general, recurrence, this is such a term in which we describe the next state as a result of the previous ones. For instance, the classical example of the recurrence string, recurrence sequence, is a Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, and so on, is such a method that the next one is the sum of the previous two. Yes. So 2 is 1 plus 1, 3 is 2 plus 1, 5 is 2 plus 3, and so on. So we can write this sequence as such a Fn is Fn minus 1 plus Fn minus 2. Of course, we should have the starting one, so we write the F1 and F2 are 1, and next we can describe just like the sum of previous two ones. This is very useful and very easy to describe in such a case the sequence. But of course, the question is, what is the nth element? Of course, we can calculate all of them up to this Fn, but if n is 10 to the power of 600 centezillion, it can be slightly difficult. Of course, okay. So let's start from this Hanoi towers as the example. maybe let us describe recurrence as such a statement that the solution of the studied problem is expressed by the same problem for data of smaller size. Smaller sizes. Okay, what is the Hanoi Tower problem example? Hanoi Towers. So the legend is that in some temple in ancient Hanoi, there are such sticks made of gold, as I remember. And there are a number of discs with the hole in the middle. In such a situation that there are with smaller and smaller sizes that are made of gold. And the question is it possible to move all of them in the third stick in such a method that we can always put smaller one on the bigger one? So this is the two-dimensional view. This is such a, maybe I can write it in three-dimensional. It would be something like this. Yeah, this is a smaller one, and somewhere here we have this bigger one. Somewhere here is just ground. Something like this. Yeah. Okay, so we can put smaller one on the bigger one. Such a situation like this is forbidden. Yeah, and of course it shouldn't be especially just difference but one. That means that we can put, for example, on such a big one, a smaller one like this. So this is possible, but the method is how to transfer them to the third one. Of course, for smaller sizes, we can show it just by. I think it is quite easy for two of them. Let us try, or three. For two, n equals to 2. So we have such a situation. We put this one here, obtaining something like this. Of course, we can put them on the ground also. Next, we put this one here, having such a situation, a smaller one here, and now this one here, and this is done. Sorry. So this is quite easy for two of them. And similar for the next one. The most interesting here is that, in fact, it doesn't matter what is the number of them, because such a situation like here can be described like such a ground. Yeah? in such a sense that we have two here, they are put it here, and that's all. And of course, it doesn't matter if we put here on the third one, on the second one, because in fact, we can enumerate, re-enumerate them. Yes, this is the first, the second, and the third, but other numbering of them makes the possibility that any of them can be the third. And we can change the algorithm. So, in fact, we can assume that the ground is somewhere like here, put two of them here, and next try to solve the bigger problem. So, the method of solving will be based on the recurrential thinking. But let us write the problem, as I said, on the beginning. This is just a description. So, the text. The problem in this legend, there was 64 of them. And the legend was that if it is done, the words will be Diom or something like this. And the problem is that the disks from stick A are transferred onto stick C, A, B, C, in such a way that the individually moved disks can be placed either directly on the ground, or onto a disk with a larger diameter. The question is about the number of necessary moves and the way of doing them, about the number of necessary movements shifts for a pyramid with n disks. Is it clear what is the problem to be solved? Can you hear me? Maybe something doesn't work.
Yes, sir, we can hear you.
Yes, sir.
Yes, sir. Yes.
Thank you. This was the test question. Usually I just say a joke in the middle of the lecture, but the most funny are the Russian ones, and this is the bad time for Russian jokes, so there are no jokes. Okay, so how to solve this? The proposition is a recurrential algorithm. Let us try to describe the number of moves, of necessary moves, in a recurrential way. I am visible up to which moment? Maybe like this. Okay. This is permanent one or something. Some of these markers are very difficult to erase. Maybe I will remove them. Okay, so let it be NM will be number of moves from K. Number of moves. In fact, we write it in such a way, shortly, number of moves. Such a notation means number of this hash. 4K disks. As we have seen here before, we need 1, 2, 3 moves to solve the problem with n equals to 2, but we can also describe it for smaller sizes. Let us imagine like something like this. Just a second. For n equals to 0, we have 0 disks and a number of moves, and m from 0 is 0, because there are nothing here on the ground. For n equals to 1, we have the algorithm for 1, and it is consisted of only one step. Step 1, move disk onto C. Just here, one disk. So the number of moves here, number of moves for 1 is 1 move. For 2, we have described before. So this will be algorithm for 2. It consists of 3 steps. Move the 2 of them, so smaller and bigger. Move smaller onto B. Step 1. Step 2, move bigger onto C. And step 3, move smaller onto C. So the number of moves for 2 is 3. Okay. So we can observe that in fact, if we move the smaller one here, where's the black one? If we move the smaller one here, let it be okay here. In fact, we need such a situation that some of these disks should be equal in some sense with the ground. So if we have such a situation that we can put everything on the disk, it is like being a ground. Yes. So the thinking is, let us try to make it in such a method to move something and next solve smaller problem. And smaller problem we can solve for instance for 2 of them. Yeah, it can be visible like something like this. Yeah, that we have such a ground with such a step here. Yeah, that this is a ground, and of course we can do everything here because this is the ground. But a ground is in fact the disk, but in such a big size that we can put on this everything. So this is a method of thinking about solving this problem. Solve smaller problem because everything lower on the lower level is bigger. Okay, just let's try to make the algorithm for 3. n equals to 3, algorithm for 3. It will be something like this, maybe here. Maybe I will write a number of them. 1, 2, 3, 4, 5, 6, 7. This is a ground. One, 2, 3, 5. I have written 7 steps because I know that it will be 7. Okay, so let us try. So we have 3 of them. Firstly, we put the smaller on C. Next, we put the middle one on the B, and smaller one on B. Something like this. So in fact, we have such a situation that we have moved this bigger part of the pyramid to the B. Now we can just move the biggest one on the C, and this will be the ground for this moment. Yes, because we have such a situation like here. This is of course this middle and smaller one, and for us here, in fact, is a new ground like this with such a steps. Yes, this is a new ground because it doesn't matter. This is the biggest one. We can forget about them because it doesn't matter. We can put on this everything. Okay, and now this is just the problem of move this smaller pyramid from B to C, but we can do it because we have such a procedure. This is this one with using the temporary one. For now, in this step, the temporary one was B. Yes, this was the temporary. We just use it in the computer programming, for example, in the C language or any other, like TMP variable. It's not just temporary. This is for using. So for now, this temporary will be here. This will be temporary because this will be for store for a moment a smaller one. So this is up to the end here. Number of steps. 1, 2, 3. Okay, this will be that one. So we just move the smaller one here. This one here, obtaining such a situation like this, and the last step, this one here, and we will have the final situation like we would like to have. But now let us thinking about this moving of the smaller pyramid. This consisted only of 2 elements, like a sub problem. So in fact, solving of moving this one to the position B, this is made by these 3 steps. 1, 2, 3. We have moved this here. Next, we have moved the smaller one here, the biggest one here. And next, the procedure is to move this to one on the third one, and we have obtained this here. So let us try for algorithm for 3, something like this. This is maybe let us write it in the steps, but with some observation. So like here, this one, and this one, it can be written like algorithm for 2. Yes. Next, we have moved the biggest one. This will be step 4, yeah, because 3 of them are here. Step 4, move biggest onto C, and next, once again, algorithm for 2, because this is algorithm for 2 of them. Yeah? This is 3 steps This is 3 steps. This is 1. So in general, we have a number of steps 7 here. Is it clear? How does it work?
Yes.
Yes, sir. Yeah, thank you. Okay, if we write more elements of the sequence, we'll observe such a increasing of the number of steps. If we write it in such a way, n and the number of moves from n. For 0, this is 0. For 1, this is 1. For 2, it's 3. For 7, it is sorry. For 3, this is 7. For 4, this is also easy. When n equals to 4, we'll have something like this. This will be algorithm for 3 for moving such a 3 of them on one of them. Next, this is 7 moves. We have step 8, which is move the biggest onto C, and next one algorithm for 3. So algorithm for 3 takes us 7, 14, 15. So now we see what is this for every computer scientist. It is very clear what does it mean. It is 2 to the power of n. In fact, here is to the power of n minus 1. Yes, because we have 2 to the power of, no, to the power of 4, sorry, n minus 1. Yes, because this is 16 minus 1, this is 8 minus 1, this is 4 minus 1, this is 2 minus 1, and even this is 1 minus 1. So this is just clear what this is. But from if we would like to write it from this observation, we write it in such a way: number of moves for n is number of moves for n minus 1 plus 1 and plus number of moves for n minus 1. So we can write it in such a recurrential equation. Number of moves for n is 2 times number of moves n minus 1 plus 1, with the initial condition number of moves for 0 is 0. And this was what we called recurrential equation. In general, solving of recurrential equations is not an easy task. We'll talk something about this, but really this is hard task sometimes. We should use some method, but we'll talk about it today. Sometimes we can just guess the result, last here. Yes, this is just easy because we can just 2 to the power of n minus 1. So it seems nice, but in general it can be difficult. Have you any question to this part of the lecture?
Oh, sir, thank you.
Okay, so let us make a short break now, because I have to put some present to this man who finished the job today. I have some present in a form of alcohol. So this is for a man. For women, this is usually flowers, but for men, this is alcohol. So I should ask a present, say something, and I will be in 10 minutes. So sorry for a little bit earlier break. A short break for end of a 50 years job. I'm back. So we are with the recurrential equations and recurrential procedures. Can you hear me? Is it okay with the sound?
All great, sir.
Oh, thank you. Of course, we should remember that recurrential formulation of problems of solving problems by algorithms is quite time consuming for and quite hard for computer hardware software, in the sense that we need a special data structures for storing the situation to come back to the previous situation. So to write the recurrential formulation, of course, we need initial condition like here, but also sometimes some additional storage. Let us try to write it on the Fibonacci sequence example. Example 2. F1 equals to F2 is 1. Fn is Fn minus 1 plus Fn minus 2. Sometimes it starts from 0. Just a second. Let us try 0. This will be 1. This will be 1. So this is 0. Yeah, okay, Fn. Okay, so for instance, so as you remember, 1, 1, 2, 3, 5, 8, 5 plus 8 is 13, 21, 29, 34, 55, 89, and so on. This is the recurrential formulation. Of course, we have also the non-recurrential one. It is for Fibonacci. This is quite strange. I will write you. This is recurrential one, recurrential, non-recurrential. Fn is 1 by square root of 5. 1 plus square root of 5 divided by 2 to the power of Fn minus 1 minus square root of 5 divided by 2 to the power of n. So it looks strange. Why? Because the result of such an equation is always natural number instead of this square root of 5 here. Square root of 5, as you remember, is this is not a quotient of, so this is non-relative number. Let us try for a moment to check if it works, because for me this is a kind of magic. If we have such a formulation, let's try to find out what is then for let it be f equals to 2. So we have 1 by square root of 5, and now here 1 plus square root of 5 square divided by 2 minus 1 minus square root of 5 to the second power divided by 2. Okay, so we can get the common denominator too. So this will be 1 by 2 square root of 5, and here we'll have 1 plus 2 square root of 5 plus 5 minus, here will be 1 minus 2 square root of 5, by this one, plus 5. Okay. So we'll have 1 by 2 square root of 5. Here we have 1 minus 1. This is 2 and this is plus plus, so this is 2. So this is 4 square root of 5 and plus 5 and minus 5. So this is 2. This is square root of 5. Finally, this is 2. So this is for me a kind of magic. Of course, this is not a real magic, but the mathematical magic in the sense that we have plenty of square root of something, but finally we obtain natural number. And this formulation is quite difficult to guess. Yes? If we just find out how to write such a formulation for Fn, for any n, this is Fn. This is not possible to just guess how to write it. By the way, such a proportion like 1 plus or minus the square root of 5 divided by 2 is in mathematics called gold proportion. Gold proportion, this is such a proportion which we can observe, for instance, in some natural plants, like such a one that we have leaves here, and the sizes are smaller and smaller, and the proportion between them are like a golden proportion. Yeah, for instance, this one to this one, golden proportion, golden proportion, and this is golden number. But this is just a name for. We can find a number of them. I have some somewhere here. Oh, just a moment. Golden proportion. Because this is just an interesting one. 156. If we observe a proportion in ancient sculptures, as well as in the plants like here, yeah, and in human face or arm, yeah, there are in every situation there is a golden proportion. Golden proportion, even in the ancient temples. Yes, a golden proportion is given by the square root of 5 minus 1 divided by 2. It can be written like as also 1 minus square root of 5 plus 1, or by such a infinite fraction. So in the nature, this is very well known, but here in the Fibonacci sequence, it is quite difficult to understand how it appears here. Okay, so how to obtain such a solution of the recurrential equation? Let us start it today. I don't know if we are able to finish it today, but because it is quite hard. But let's start. I will write it as methods of recurrential equations solving, and we'll try to show some examples how to obtain it. Recurrential equations solving. Let us imagine an example. Let us consider a referential equation given by such a formula. An is 2 times an minus 1 plus 1. For n greater than 1, with the beginning value a1 equals to 1. So on the beginning we have starting elements of the sequence are 1. Next we have 2 times 1 plus 1, this is 3. Next we have 2 times 3, this is 6 plus 1 is 7. Next we have 2 times 7 plus 1 is 15, 31, 63, and so on. Of course, we know this sequence. In the previous one, we have had -1, but let us try to show how to solve it analytically. So we're interested in finding an algebraic equation for calculating any element of this this sequence. This method, which I will show now, is called substitution method. Why? Because we can write the elements of this sequence in such a way. Let us try. So we write an as 2 times an minus 1 plus 1. But from this equation, we can write it in such a way that this is 2 times, and this an minus 1, we can also write from this equation as 2 times an minus 2 plus 1 and plus 1. Of course, we can write it in right order in such a method. This is 4, so this is 2 to the power of 2, right? Times an minus 1 plus 2 and plus 1. Okay, now let us try to write this element from the recurrential, so now also from this equation. So we'll obtain 2 times is 2 squared times an minus 1, which can be written as 2 times an minus this is here 3, yeah, plus 1, and this can be written as 2 to the power of 3 times an minus 3, plus here we'll obtain 2 squared, plus here 2 to the power of 1, and plus this 2 to the power of 0. And finally, after 3 dots, which are the most skipping in this situation, because in fact we just write and so on. So after this and so on, we'll obtain that this will be 2 to the power of 2 to the power of what will be the number of steps? If we have n minus 3 here, we'll obtain here 1 less. So if we finally write to the end, we'll obtain that this is 2 to the power of n minus 1 plus 2 to the power of n minus 2 plus 2 to the n minus 3 and so on, plus 2 to the power of 2, 2 to the power of 1, and plus 2 to the power of 0. And now, such a sequence can be written in a very easy way. Maybe I will remember you quite easy equation from primary school, probably. So as you know, if we have a plus b to the square, this is a square plus 2ab plus b squared. Similar, if we have a plus b to the power of 3, this is a to the power of 3 plus 3a squared b plus 3ab squared plus b to the power of 3. You remember these equations? Question tag?
Yes.
Yeah. Okay. So in general, we have such a thing. The a plus b to the power of n is given by such a formula. N by 0, a to the power of n, a by 1, n by 1. This is a Newton symbol. The n by k in general is n factor divided by k factor n minus k factor. Also, this is recurrential one, but it doesn't matter here. Plus a to the n minus 1 times b plus 3 dots n by n a to 0 b to the power of n. Oh, okay, in fact, this is b to 0, and here we have a to 0 b to n. Of course, we can write it in very easy formula, just a sum of n by k from k equals to 0 to n, a to the power of n minus k, b to the power of k. Okay, so this is a general formulation for this shortening of multiplication equations. But if we put here to this equation 1 plus 1, let us observe 1 plus 1 to the power of n. This will be n by 0, so this is 1, a to the power of n, so this is 1 to the power of n, b to the power of 0 is just 1. This is okay. Just a second. This is a little bit difficult. Oh no, maybe this is not. Okay, so this is n by 0. This is 1 plus n by 1. This is also 1 plus n by 2. This is also 1, and so on, plus n by n. I don't know if this is a good equation here. Now, okay, this is 2 to the power of n by, but this is a wrong approach here, because this is true, but this is not compared with this one. No, we should make it in another way. Maybe this is also true, but okay, this is not needed. Wrong way. This is true, but we don't need this equation in this moment. This is from Pascal triangle. But let us look once again here. So we have something like this. That this is 1 plus 2 plus 4 plus 8 plus 16 and so on. So the n times, in fact, n plus 1 times, because this is to the power of 0. So the question is that this is 2 to the power of n minus 1. Why? Because in general, this is a geometrical sequence, geometric sequence. And maybe you remember that if we have a sequence with the multiplier q, the sum of this of geometrical sequence is 1 minus q to the power of n divided by 1 minus q. This is the sum of geometrical sequence with multiplier factor, maybe q factor. So the q here is 2. Q is 2. So if we put here like this, we'll obtain the sum of this sequence will be Of course, it can be also written in the another way, because this is also q to the power of n minus 1 divided by q minus 1, because this is minus minus, it doesn't matter. Yep. So we obtain here that this is 2 to the power of n minus 1 divided by 2 minus 1. Yeah, so it doesn't matter. And finally, we'll obtain what we need. So this recurrential equation can be written in such a general form, analytical form, without recurrential insight. And this is the main task of us in recurrential situations, that we need a non-recurrential form of the equation, and this is the way. Yeah. So one method is substitute up to such a moment that we have the whole sequence. In general, it looks easy, but sometimes it is not. We can try in another situation. Of course, we can check if it is true, but in fact, sometimes, like here, this is very easy, sometimes it's not. Let us try another situation. This will be another sequence, more general situation 2. So let us consider a recurrential equation given by such a formula. Sn is a times Sn minus 1 plus b times Sn minus 2. So this is a generalization of the Fibonacci, because in the Fibonacci sequence we have only a and b as 1. So case A. So let's consider that A or B are 0. It is quite easy, because this will be probably the geometrical sequence, but let us see. Of course, we need here with known values of S0 and S1, and A, B are constant. Yeah. So if B is 0, then Sn can be written as A times Sn minus 1, and for n greater or equal to 1. And finally, if we substituting, so we'll obtain that S1, this is A times S0, S2 is A times S1, so this is A squared times S0, and finally Sn will be A to the power of n times S0. So this is quite easy if one of them is 0. Of course, if A is 0, similar, if A is 0, then similarly A just a second. If A is 0, it is more difficult a little bit, because this is n minus 2 here. Yeah. So if A is 0, so we have such a formulation as Sn is B times Sn minus 2 with the difference 2. So we'll obtain such a thing like this. So then Sn is B times Sn minus 2 for n equals or equal to 2. So we can write that S2 is B times S0, S4 is B times S2, and so this is B squared times S0. And finally, we'll obtain that with the index 2n is b to the power of n times s0. Similarly, we have that s3 is b times s1, s5 is b times s3. So this is b squared times s1, and finally we have s with the odd index 2n minus of plus 1, 2 times plus 1 is b to the power of n times s1. So we have the formulation for even and odd ones. Andrzej, mam wykład, odsłonię to trochę. Dobra, dzięki. Okay. Sorry. So we have the equations for 2n and for 2n plus 1. So in fact, we have for all natural numbers. So this is quite easy if we have 0 somewhere here. But if it is not, this is more difficult, but let's try. In fact, we are looking for some kind of general approach to solving such a recurrential equations with linear factors, yes, without any squares or something. Okay, so example, the next one, next. I have written here 36, example 36. Maybe yes. Sn equals to 3 times Sn minus 1, where S0 is 5. So let's try. From here we have that this is B0, A is 3. So finally we should have something like this. So Sn should be 3 to the power of n times S0, and 0 is 5, so this will be like this. Okay, another one example. If we have Sn equals to, let it be 3 times Sn minus 2, and the starting conditions S0 is 5 and S1 is 2. So we have the case A0, like here, yes. So we have two formulation, in fact, consisted in two equations. So we have for even one, for even n, we have S to n will be B is 3 to the power of n times S0, so times 5, and S with the index 2n plus 1 for odd 1, for odd n, we have S2n plus 1 equals to B to the power of n, so 3 to the power of n, times S1, which is 2. Okay, so it is quite easy. But if A, so this will be case B. Case B is that A is different than 0 and B is different than 0. So this is quite hard, and we can try to show some methods today, but in fact we'll continue it on the next lecture. We'll need something which is called characteristic equation. But first, let us try solving some example. Yes. Example. So let us consider something like this, that we have an given us an minus 1 plus 2an minus 2 with initial conditions, that A0 equals to A1 is 3. So this is our equation. Similar to the Fibonacci one, but in Fibonacci, there is no 2 here. How the elements of this sequence looks like. So if we start from 3, so we have n here and this sequence. Sequence 2 asterisks. So for 0, this is 3. For 1, this is 3. For 2, we have, this is the previous one, plus 2 times this one. So this will be 3 plus 6. So this will be 9. For 3, we should add this one and 2 times this one. So this is 9 plus 6. So this is 15. For 4, 15 plus 2 times 9. So this is 18 plus 15. So this is 33. For 5, this one plus 2 times this one. 30 or 33, this is 63. And so on. As it looks familiar somehow, we see that here, here, and here we have almost 2 to the power of n. But the rest looks more difficult. So we obtain, I will write the general form, an. This will be 2 to the power of n plus 1 plus minus 1 to the power of n. And this will be general solution of this equation. But why and how to solve it, I will show on the next lecture. Because for showing the methodology, we need some more mathematics approach and showing the recurrential, the characteristic equation of the recurrential equation. In general, recurrential equations are a very hard part of the discrete mathematics. We can solve linear ones, as here, but if we have some squares here or another function inside, this is just guessing for the result. Of course, the question is if we really need such a final form of the recurrence without recurrence, yes, an analytical one. This is where we need it. Of course, we need it if we would like to calculate the number of steps of the algorithm. For instance, if we have a Fibonacci sequence, once again, the function of calculate the Fibonacci sequence in C language, it will be something like this. Fibonacci, we have inside here n, and it looks something like this, that if n is 1 or n is 2, this will be just return 1. Yeah. Else, if we have something else, we just return Fibonacci of n minus 1 plus Fibonacci of n minus 2. So this is a recurrential one. We just return this plus this, and inside we should calculate once again. Of course, in the computer programming languages, we need an initial condition to end the recurrence. But if we ask a question, what will be the number of steps to compute, for instance, Fibonacci of 1,000? Yeah? Not the value of them, but the number of this function call. So the answer will be Fn. So the number of this, and we need the form without recurrence. So this is why sometimes we need just a form without recurrence, like here. But in general, this is difficult. On the next lecture, I will show how to solve the case, this one. Next lecture. And we'll have some tools for solving sum of recurrential equations, especially this Fibonacci one. But as I said, in general, for not linear one, this is much harder. Have you any questions, remarks? Okay, so this will be the end for today. A little bit shorter because this part takes me for this case about an hour, I think. So I will start it on the next lecture to not break it inside. So thank you very much and see you next Tuesday. Thank you.
Thank you.
Bye.
Thank you.
Thank you. Goodbye.
Bye.